high-speed internet, telephone calls. Now, information like that is sent through these fibers in the form of light. This means a computer generates a code. That code is translated into fluctuations of a laser beam, and the light signals are sent along a network to TVs, computers, and mobile handheld devices. So to give you an idea of how much information we're talking about, this one tiny strand of glass has enough capacity to carry more than 500,000 phone calls, all at the same time. Now, I have to admit something. That was the number when we built this display 10 years ago. From modern advancement up until today, that number has changed from 500,000 to 10 billion. That is everybody's phone call on the planet at the same time, plus another 3 billion. Now, before we had the fibers, up till today, we've been relying on copper wire to do the same job. But do that job in copper, you'd have to use that entire bundle you see on the wall to your right. There's more than 1.5 million strands of copper there. But again, that's the display when we built this display 10 years ago. To do that same job in today's advancements, it'd be like filling the Grand Canyon with copper wire. So just from the sheer scale of things, you can see how much of an improvement we'll be talking about. Now, like I said, all this information is sent in the form of light, which really means we're just communicating with light. Now, you understand that that's possible because of basic examples like the one you see here. But doing the same job in a tiny strand of glass is just a little more challenging than using lighthouses. To do this, we have to exploit an ability the glass already has. That ability is called total internal reflection. Now, admittedly, at first glance, internal reflection here looks kind of complex, but in about 2 minutes, that's going to make perfect sense, I promise. You see, internal reflection just relies on the fact that light will travel at different speeds through different material. So, for a moment, let's consider the term speed of light. That refers to how quickly light travels through open space or air. That's incredibly fast, 671 million miles an hour fast. But light will travel slower than that through things like water and glass. You see, it seems light prefers to move at a slower pace, along a path of greater resistance. So when light is traveling through these slower materials, it's internal reflection that helps to keep the light trapped inside of them. That's basically how we get your information to stay in and communicate through tiny threads of glass. Now, I could spend all afternoon explaining this with the math and everything, but seeing is believing, right? So, to better highlight this point, we're going to turn our attention to a few examples. The first experiment involves these 2 tanks of water and a slide projector I've got turned on behind the first one. The beam of light in our projector is focused to a tight, narrow stream, pointed through the water into the back side of that tap. So when I open the tap, of course, the water will flow into the lower tank. But wouldn't you also expect that beam of light to just continue on its straight path out along the wall over here? Well, let's open it up and see what happens. Okay, you see the water flowing out, but you don't see the beam of light. Now this is because the light is trapped in the slower moving material. Within the water, light is reflected internally. Now I could show you the light just by breaking that stream with this board. If you break the stream, the light escapes, so this board lights up a bit. But if you don't break the stream, then this light you see escaping now simply stays trapped in the slower moving material, so it follows the path of the water along the curve. It makes all of this a great example as to how internal reflection works. You see, that's the very fundamentals to how optical fibers function for us, just by keeping light trapped in a slower moving material. So in this example, that material is water, but in optical fiber, that material is our glass. So, now that you've seen this one, let me turn it off. This will bring us to our next experiment, which involves my fancy green laser and a small tank of water on the counter. Now, when I fire the laser through that water, we don't really see anything that surprises us. That light pretty much does what we'd expect. Starts here, ends there, stays on a straight path. But watch what happens when I redirect this laser beam up to try to get the light to break free of the water and escape into open space. Now, you'd expect the laser just to pop out of that tank and hit the wall, right? But when that light hits the surface of the water, it reflects back down into the water, into a path of greater resistance. That's internal reflection at work. What's happening is at this interface where water ends and air begins, right there forms a natural phenomenon called a perfect mirror. This mirror reflects the light back down into the water. Now, you've seen this before if you've ever been swimming. You know how if you hold your breath, you can swim underwater and then look back up to the surface and see a reflection of what's underwater with you? Well, that same thing's happening in your swimming pool. That too is internal reflection. You see, I told you this would start to make sense in like 2 minutes. Okay, so you've seen the concept through water. That's kind of fun, right? But we're talking about sending our information in the form of light through glass, because that's what our fibers are made of. So to give you an idea as to what that looks like, I've got a solid block of glass here on the counter, got the laser pointed right through it, and just on the other end I have a video camera. So through the magic of television, on our big screen, we're going to get an internal view as to what light looks like traveling through this block of glass. So when you look at the block on the counter here, you can just about see the laser traveling through it. This means a small amount of light is escaping that glass and reaching your eyes. But most of the light is reflected back inside the block off these internal surfaces. So we could try the same trick where we try to get that laser to break free of the top surface of this material. But just like in the water, when the laser hits the glass, the mirror is formed, so the light is reflected internally. That makes this a large-scale view as to what it actually looks like inside of an optical fiber, with all of your information, those light signals traveling through them. So this trick with internal reflection here, this works in all types of glass. But some glass will transmit that light better and further than others. So we measure any material's ability to transmit light well on a scale called optical purity. Now to give you an example as to how the purity scale works, I'm going to show you two very different samples of glass. The first sample, it's called soda lime glass. Drinking glasses, light bulbs, windows, all that ordinary stuff is made from soda lime. And it's also all pretty far down on that scale of purity. You see, what I mean is, you think about your windows back home as being clear glass, because light travels right through them, no trouble at all. But if you've ever looked at your windows on the edge, you can see that the light has a little more trouble getting through that way. You also notice, it's not clear glass, it's green glass. Now you're seeing all of this because now we're looking through a more significant thickness in the material. This green is caused by the buildup of iron impurities that are inherent in the manufacturing process. So if you look through a sample of this same stuff at a thickness of 3 to 5 feet, well at that point those iron impurities become so numerous and dense, light can no longer penetrate the glass at all. It wouldn't look green anymore, it'd look dark blue, maybe even black. So realistically, when it comes to communicating our information in the form of light through glass around the world, well, 3 to 5 feet's really not that practical. Luckily for us, scientists at Corning developed this type of glass, high purity fused silica. Now this stuff is all the way at the top of the purity scale. It's so clear and so pure, you can transmit those same light signals through this glass at a range of 125 miles. So, it's 125 miles of communication, or just 3 to 5 feet. I think the official scientific term here is a no-brainer, right? See, it was actually a combination of both the invention of the laser back in 1960, then the development of this glass by Corning scientists in 1970, that had made optical fiber communication a possibility at all. Okay, so I just told you about how clear and pure these strands of glass are, but they've actually got another amazing ability I know you're not going to believe. What if I told you this little bit of glass is incredibly strong? Now glass, like any material, will break only at its greatest imperfection, greatest impurity, or its greatest flaw. But as you can see, because it's made from such a pure material, and such a pristine surface, there are no imperfections or flaws. There's literally nowhere for that glass to break. That makes this fiber so tough, you could tie this solid piece of glass into a knot. A little strange for solid glass, right? I mean, you generally consider that to be pretty fragile stuff. Do you also sometimes think of maybe steel as being a benchmark for strength of material? Well, surprise, we discovered that the optical fibers are in fact 3 times stronger than steel. Now, that's pretty impressive for a simple strand of glass. Okay, so I just called it simple, but it is a little more complex than what you can see right here. Wrapped up in that tiny fiber, there are 3 crucial components. The first part, most importantly, is the core. This is where all your information is transmitted. Now to help those light signals along the way, we coat that solid core with a slightly different type of glass. This first layer, called the cladding. Now, the reason for this multi-layer thing, you see, we're trying to emulate the same results we achieved in our experiments. We need the mirrors to form so that that light stays reflected internally. Those mirrors only appear where one material ends and another one begins. So the differences in those 2 types of glass is the same idea. This surface where they meet forms the mirrors and becomes incredibly reflective. Now I've demonstrated for you how tough it is, but if you scratch it, we've got a flaw. That's where it's going to break. So to prevent that, we include an outer plastic coating, there to simply keep the fiber clean and free from damage. Okay, so you've seen what it is and I showed you how it works, but why does it matter? What's the big deal, right? Well, the big benefit we're looking to gain through the use of the fibers is an increase in bandwidth. Now, bandwidth is a measurement of how many information signals you can send through a network at any given time. If you send any information at all through that copper wire network, you'll have to do that roughly 1 electrical pulse through 1 copper wire at a time. That means one TV station, one page of the internet, one cell phone call at a time. Now, it's done this way because if you send electrical pulses too close together, they interfere, you lose your information entirely. This obviously pretty well limits the amount of bandwidth you can gain through copper. But because we can send our information in the form of light through a network of these glass fibers, and because light could be broken down into so many different wavelengths, here you see the 7 colors of the rainbow, the wavelengths of light you see with your eyes. There's actually several hundred more of them right here that you don't see. But we could send your information on each and every single one of them. Then we could group together any number of these light signals and send them in opposite directions at the same time through a single strand of glass. You see, unlike those electrical pulses, you could send light signals as close together as you want. They don't interfere with one another. And it's because of this that even up till today, we have still yet to reach the maximum information capacity of a single optical fiber. This grants you unlimited bandwidth. That is a huge improvement over that copper. So to help you quickly visualize what all this unlimited bandwidth actually means for us, we're going to take a look at one last slide. Now this is our comparison slide of high-definition television. And you love HD TV because it looks great, right? But if you watch it long enough, you notice when that picture gets complex or fast-paced, you sometimes just see a breakdown in the signal, like a fuzzy distortion or a small blocky effect. Sometimes your picture will freeze or go blank completely. You guys have seen that before, right? The reason this happens, there's nothing wrong with your television. Don't get mad and throw it out. It's just simply not receiving all of that information fast enough to piece together this complex picture. So here it is. The reason your TV doesn't receive the signals fast enough is because somewhere out there between your provider and your TV back home, there's still a network of copper cables out there. It's sending all of this complex information, one electrical pulse through one copper wire at a time. That's constricting the flow of signals. It slows everything down, leads to that deformation of picture back home. But as we go forward in the next couple of years, you're going to see a lot less copper and a whole lot more optical fiber. That you will never see distortion in TV signals. Your telephone calls will be more clear and consistent, and our connections to the internet will seem instantaneous. Now, there's only a few places right now, like in major cities, where you can even come close to getting a direct connection. But as we replace that outdated system more and more with the fiber, then we all only have to benefit from that. So hopefully now you have a better understanding to what the fibers are, how they work, and why we're headed in the direction we are with our communication networks. So if you have any questions, just come on up and ask. If not, thanks for listening, and thank you for your interest.